to chapter 16, which once again is, I guess will be exam 3 stuff. Yeah. Um, so we're going to talk in this chapter about some thermodynamics. We are coming down the roller coaster hill of the hard stuff, and we're now going to get some chapters that maybe a little bit like normal. There's a little bit more formulas, some stuff to kind of pick out to use and stuff like that. Maybe not so hard on the conceptual stuff. So here we're going to talk about entropy, free energy, and equilibrium. So we're going to use a little bit more of the alphabet here in this one. We're also going to pull from old time's sake there, delta H, which is again the change in enthalpy. And that's basically the heat of a reaction. And that's really the first law of thermodynamics, which has a lot to do with the energy, which you talked about in the previous class. A reminder, right, if our delta H value is a negative value, then we're looking at an exothermic process where heat and energy is released. And vice versa there, if our delta H comes in with a positive sort of value, that's going to mean we're looking at an endothermic process. And that is when heat and energy is absorbed in that case. So again, sort of the conservation of energy. Energy cannot be sort of destroyed nor created, but can be transformed from one form to another, and sort of a perfect exchange of energy. We oftentimes think about it in chemistry. If again somebody loses a certain amount of energy, there should be somebody gaining that energy along the way. And we're going to talk about some of these other ones here. We're going to talk about entropy, which is delta S. We'll talk about free energy, which is delta G. And of course, this class would not be without our favorite letter ever, which is K. And we'll tie these things to the equilibrium constant at the end. So let's talk a little bit about spontaneous processes and spontaneous physical and chemical processes. And one of the important things to sort of think about when we talk about a reaction being spontaneous, which a lot of times in this sort of chapter, that's sort of one of the questions that you're sometimes often asked is, would you expect this reaction to be spontaneous? And sometimes people have sort of a wrong idea about what that means when we say, yeah, this reaction is spontaneous. Sometimes people think when you say a reaction is spontaneous, you like snap your fingers and boom, it just happens really, really fast. And that's not what we're really talking about in this context here in thermodynamics. So when we talk about a reaction being spontaneous, what we're really referring to is the idea that under those specific conditions, that reaction should take place without any outside sort of interference to help it take place. It should just be able to sort of happen and take place. And that could be a reaction that happens really fast. It could also be a reaction that happens really slow as well. It could be anywhere in between. So when we're talking about thermodynamics, again, we're really referring to and sort of talking about, will this reaction occur? And in most cases, if we think a reaction is going to be spontaneous, what that usually means is when we look at the equation, that reaction is favored to go from reactants to products, kind of in the forward direction towards our product side. If it's a non-spontaneous reaction, what it essentially means is that reaction is not favored to sort of occur. So under those conditions, you can leave it all day forever. It will just really not happen unless you kind of help it along. Some type of outside interference has to do that. So when we're talking about sort of spontaneous, that's really what we're looking at. We're not really talking about how fast or slow the reaction will take place. When we talk about how fast or slow the reaction takes place, that's what we talked about in the very first chapter, which is kinetics, right? It's how fast or slow the reaction will take place. But here we're just really looking at that sort of situation. So obviously water runs downhill spontaneously. If we take some sugar, it will dissolve in a cup of coffee. Water freezes at 0 degrees and melts above 0 degrees. Um, Heat and energy always flows from the hotter object to the colder object. So hotter object gets colder object gets warmer when they do that. Iron, when it's exposed to oxygen, a little bit of moisture is all you need for rust to form. Clearly, if you're skiing, all you just need to go over the hill and you're going to spontaneously make your way down the hill. If you want to go up the hill, which probably this person is not very happy to see that happening right about now, you cannot just stay at the bottom of the hill and you're just going to magically go up, right? You got to do something, some type of work to get yourself to get up the hill, and that's sort of a non-spontaneous process. Same idea here. If we had some gas molecules separated by a little valve and we open the valve spontaneously, these gas molecules, because they have energy, they're going to fly to the other side and kind of fill the other chamber there. If we were starting with that situation just by leaving it alone, is probably not a good chance that they're all going to decide, hey, let's all go vacation over on this side, and they're all going to leave this side without, again, some type of outside interference or some type of outside way of making that happen. So, does a decrease in enthalpy mean a reaction proceeds spontaneously? And the idea here also is sometimes people think that we can just kind of look at delta H and it being exothermic is like we're going to get a spontaneous reaction in that case. And that's not always the case. So delta H by itself, or the change in enthalpy, is not a factor that we could use solely to determine whether or not a reaction will be spontaneous or not, as all these reactions here are spontaneous reactions. And you can see on some of these reactions, we do have some exothermic sort of situation happening here with a negative delta H. So combustion reaction, the formation of water. We also see here some endothermic results, and these also are spontaneous reactions, especially the third one there, that is ice melting to liquid water. We've all perhaps taken an ice cube out or had an ice cube out, and it's just going to start to melt, right? You don't really have to do much to it. You don't have to technically heat it up yourself or add any extra heat. It's just that flow of energy from hot to cold is what happens, right? Because the room temperature air is hotter than the ice cube. So all the energy from the air goes into the ice cube and it starts to melt. So looking at just enthalpy, delta H, is not necessarily the sole factor that we need to look at to determine whether or not a reaction will be spontaneous. But exothermic type reactions, and being exothermic, does favor spontaneity. So there's kind of two really big factors usually that kind of helps in things being spontaneous, and that's sort of a flow, an increase in the flow of energy, and sort of an increase in kind of the flow of the substance as well. And that really helps with reaction being spontaneous. So one of the other thermodynamic sort of properties that we could look at to help us decide whether or not a reaction will be spontaneous or not is what is known as entropy. And entropy is S, and oftentimes we see it as delta S, which is the change in entropy. Oops, change in entropy. Again, not to be confused with enthalpy, which is delta H in this case. And entropy actually measures the amount of randomness or disorder there is in a system. And as the amount of disorder increases, the amount of craziness and nutty things happening, the entropy will also increase. So as you see an increase in disorder, your entropy will actually increase. Now, kind of an unusual maybe characteristic of that is a lot of times we, again, for example, with exothermic, associate negative as exothermic things happening. But actually with entropy, when we see an increase in the disorder, the entropy value actually gets more positive. So the more disorder you have, the change in the entropy will actually become a more positive sort of value. And vice versa, as the amount of disorder decreases, which by default would mean the amount of order is increasing, our delta S value will actually become more negative. So more negative on a delta S means we're creating a lot more order. More positive delta S will mean there's a lot more disorder. What are some easy ways to sort of figure out how something is becoming maybe more disorder or ordered? The change of state is a very easy one to sort of visualize. Clearly in the solid state, right? Everybody has a lot less energy. Everybody's packed in pretty tight. It's pretty ordered, right? You got some ordered, for example, if you have an ionic solid, there's long range order as to how they're all packed in there. And there's very, very ordered. And that would have a very low entropy value because it's very, very ordered, not a lot of disorder happening. When we move to liquid state, things gain a little bit more energy, things start to move around a little bit more, and that's increasing the amount of disorder there was in comparison to the solid state. And we would start to see the entropy start to increase in that case. And when we get to the gas phase, everybody is broken apart from each other. Things are flying around. So I often think about in this chapter how many things are flying around in my face, right? So you got a lot of things flying around in your face, a lot of craziness happening, a lot of disorder. So obviously things have a lot of energy, a lot of movement happening, definitely in the gas phase, and a lot more disorder happening. And we see an increase in disorder. So in the gas phase, things have a lot greater amount of entropy than they do in the solid state. And one of the ways that we could calculate the sort of change in the entropy or look at the change in the entropy is the difference between our final entropy and our initial entropy. If you remember, there are things like delta H, delta S, and those guys, those are things that, again, are state functions. And state functions really don't matter how you get there. Again, as we'll see, I think the slide will be in here as well. But what really is important is where you start and where you end. And that is where we oftentimes will take the difference of what's happening there between, say, the enthalpy value, the entropy value of final minus initial. When we think about a reaction, and we think about a reaction that occurs, our reactants goes to our products. And really, this is our initial state. This is our final state. And that's why, as you may remember, right, if you want to calculate the delta H of a reaction, you take all the delta H of your products minus all the delta H of your reactants. And you're basically taking the difference between the final state and the initial state. And that's why we do that. Any questions on that there? Now here, as we go again from solid water, which is ice, to liquid, that's an increase in the disorder, and we would expect our delta S value here to be a more positive value as we are, again, creating a lot more disorder in that system. Now, when we talk about disorder, it is related to probability, and a probable event is one where there are multiple ways that you can accomplish that. An improbable event is an event where there are very few ways that you could sort of accomplish that. So let's just say there was like 4 doors in this room and we had to exit this room. It's pretty probable that we could all get out a door pretty much and leave this room. If there were no doors in this room, just a small little window in the upper corner, there's probably less probability that we all get out of this room. Happy thoughts today as we talk about that. But again, a lot less chance of us getting out of this room. And when we talk about ordered state, there's a low probability of that occurring and a low entropy. A disordered state, there's a much higher probability of that occurring and a larger amount of entropy. There are many, many ways you could screw something up, right? And a good chance you could increase the entropy that way. And there's only a few ways you can do something the right way, right? And get things done right and a low entropy value associated with that. Now, one of the ways that we could kind of look at entropy is what sometimes was referred to as the Boltzmann equation here. And that's the Boltzmann equation. K is the Boltzmann constant, which is kind of covered there on the bottom, 1.38 times 10 to the minus 23 joules per Kelvin. And in this particular case, W is the number of microstates. And you can think of W as the different ways that you can accomplish something or get something done. And for example, here, if we look at, say, this is like a carnival game, you got 4 balls here, and you got to want to get them all into one side here to win the stuffed animal. There's only really one way you could accomplish that. You could either put it on the left-hand side, all 4 of them, or throw them all there on the right-hand side. And since it's a carnival game, we know they're all just going to bounce out. No, I'm just kidding. Okay. But let's just say if you want the smaller prize, all you have to do is just get one on one side and three on the other. And there are four different ways you could do that. And then our participation prize here, you just need to get two on each side there, not too hard. There's actually six different ways that you could do that. Now, because there's a lot more different ways you could do that, this is going to end up with a greater amount of entropy. If you just think of sort of Boltzmann equation here, for example, since this is a constant, we don't have to worry about it in a sense. If they want to get all those guys into one side versus the other, there's only one way to do that. If we put that in there, that's a natural log of 1, which is going to zero out all that and give us a very low value for entropy. If we go down to our situation on the bottom there, where there was like 6 different ways of doing that, not 26, but 6. And we take the natural log of 6, that's like 1.79 times that. That's going to give us a much higher entropy value than it was when there's only one way to do that. And again, 4 would fall obviously somewhere there in the middle of that sort of situation. So the more ways you could accomplish something, the more entropy you will sort of have, as opposed to one way of doing something is going to have a much smaller entropy value, much more order associated with it. Now, when we look at each of these processes here, these are all processes that lead to an increase in the entropy. As we talked about before, this is basically our phase change going from solid to liquid. Again, a lot more movement. Going from liquid to gas, again, a lot more movement. Even the process of making a solution when you dissolve a solid in a solvent or a solute in a solvent, before you dissolve the solute, for example, if it's an ionic compound, it is again put together in a very, very ordered arrangement of those ions in the solid state. And by the way, before you dissolve it, say in something like water, water is hydrogen bonded with other waters before you put something in it. And that creates a nice amount of organization in the water molecules. Obviously, to get everybody to dissolve, you got to break all those water molecules, got to break apart that solid. That's now creating, again, a lot more disorder, both in the solute and the solvent in this particular case. Now everybody's free and kind of floating around in the solution. Again, a lot more movement than you had before. Also, raising the temperature, like we see on the bottom. When we raise the temperature, we increase the energy and heat in a system. And typically, when people pick up that energy, they tend to move around a lot faster, right? So, if you have a gas molecule at a lower temperature versus a higher temperature, it should start moving around and flying around a lot faster. Its root mean square velocity should start moving around and flying a lot faster than it does at that lower temperature. So, let's talk about each of these processes here and take a moment. And for each of these, does the entropy of the system change? How does the entropy change? Are we increasing the entropy? Are we decreasing the entropy? And what should the sign probably be for delta S? Should it be positive? Should it be negative? Take a moment there and think about each. All right, so let's take a look here. So condensing water vapor. So condensation means we're going from gas to liquid, I hope. And obviously we're going from a more disordered state, right? In the gas state as things are flying around to a more ordered state in the liquid. And that should decrease our entropy in this case and actually make it more negative, our delta S in this case. Yeah. Forming a sucrose crystal from a supersaturated solution. Crystal is a solid, and there's only a few ways to form a solid, and definitely that's a much more ordered situation than it was when it's floating around in the solution. And that also is going to decrease the disorder and going to make our delta S become more negative in this case. Heating hydrogen from 60 to 80, once again here, that's going to increase the temperature. That's going to cause the hydrogen gas molecules to start flying around a lot faster as they have a lot more energy. That should actually increase the amount of entropy in that system. And that would also probably relate to a delta S that's going to become more positive. And lastly, here's sublimation. Sublimation is going from solid all the way to gas. We skipped the liquid cleanup there. And obviously, that means we're going into the gas phase, which is, again, a lot more disorder. And that should end up with a more positive delta S. Any questions on those? Or... So, as I mentioned a second ago, entropy is a state function. And remember that state functions really, there's only two really important things. It's really where you start and where you end. And for these hikers, for example, the blue guy took the more direct route up the mountain. The red one took the scenic route. But in terms of their potential energy, they both basically have the same because they're both started and ended in the same location. This is the idea behind something like Hess's law, where you take all those individual reactions, add them together, get the overall reaction. Doesn't matter if it happens in 1 step, 2 step, 400 steps along the way. Entropy is a value that you can look up in a table and oftentimes need to. So in the back of your book, you usually will find a delta H table, a delta S table, and a delta G table. They're usually actually all a lot of times in the same table is where you can find those guys in the back of the book. And when you look up the entropy value in the back of the book there, like in this table here, there's a couple things that are a little bit maybe different than what you may remember for delta H. The first major difference between delta H and delta S is delta H is typically given in kilojoules, and delta S is typically given in joules. So there is sort of a difference in the units associated with both S and H. That is going to be important later on this chapter where we will see a formula where both of those are together in the formula. So you will have to do some type of conversion to convert either kilojoules to joules or joules to kilojoules. Otherwise, you will be off by a pretty good factor there if you leave them with those units. The other thing that you might remember is when you go to like a delta H of F table, which is what you find in the back of the book. When you look up things like oxygen or hydrogen or anything in its natural sort of state, those values are 0 kilojoules. But when we talk about entropy, which is S, you will actually find values for things like that. As you can see here, hydrogen, oxygen, they actually do have values, which is a little bit different than what you have when you're looking up delta H values. So typically, again, our S's are in joules, our delta H's are in kilojoules, and we can use entropy, as we'll talk about here, to help us decide whether or not a reaction is going to be spontaneous. And the first law of thermodynamics, as we talked about, has a lot to do with that energy that you talked about in the last class. But again, energy cannot be created nor destroyed, but can be converted into one form or another. The second law of thermodynamics is the entropy of the universe increases in a spontaneous process and remains unchanged in an equilibrium process. So we can use actually the change in entropy to help us decide whether or not a reaction is going to be spontaneous, but there's a certain entropy value we have to calculate, and that is what is sometimes referred to as the delta S of the universe. And basically, the delta S of the universe is made up of two things. The delta S of the system are, in most cases, the reaction, plus the delta S of the surroundings. Now, if you calculate the delta S of the universe and you do end up with a positive value, then that reaction is going to be a spontaneous reaction. Vice versa, obviously, if you end up with a negative value for the delta S of the universe, that's going to be a non-spontaneous process here. We will talk about probably next time here, since we're getting to the end, how to calculate the delta S of the system and the delta S of the surroundings. You cannot look at those individual components alone to help you decide whether or not the reaction is going to be spontaneous. You do have to add them together to get the universe to do that. In an equilibrium process, the delta S of the universe will equal 0. And it is unchanged in an equilibrium process because, as we know, in an equilibrium process, the rate of the forward direction, right, will equal the rate of the reverse direction, which means, as we talked about, essentially what happens in that case is everybody just gets locked into place, right? So there is really nothing changing in terms of disorder or whatever it is. It's just going to kind of be locked into place where they're at. And that's why, again, we'll have delta S of the universe is equal to zero in an equilibrium process. And there's not much change happening in that sense because it's just going to remain in that equilibrium position unless you do something to screw it up. And that means nothing's going to change in terms of did we make more products, reactants, everything.